Morning, I hope you can see the. Uh, Thank you very much to the organizer for inviting me here. It's a wonderful place and a very nice conference with different aspects of life. Today, I will try to show you how light can be used for rotation sensing, and when you reach an high sensitivity rotation sensing, you can test general relativity and can go into the fundamental physics realm. Point is that a gyroscope, an active ring laser, it makes a cavity, ring cavity, where a laser is inside the cavity, the laser medium is inside the cavity, so it's a sort of a closed ring where the laser travels, emits in two different directions, and this makes the Sagnac effect. Actually, this device were thought to have a certain limiting sensitivity given by the usual shot noise stuff. And the point is that we found that this limit is actually wrong, in the sense that the model, the classical model for a gyroscope that gives you the shot noise limit is not complete. And we broke this limit, but we still don't know if this is a true quantum effect, or is it just a neglecting some classical effect in the system. So let's go. So this experiment, this is a part of a big collaboration inside the INFN, the Ginger collaboration, and this part in particular is developed by Francesco Giovinetti, a PhD in Naples, actually in Wien, and David Vitali and myself. So first I would like to go briefly on what is a ring laser gyroscope. Then I will show what is the aim of the Ginger experiment. And then we will talk about Gingerino, the prototype of the Ginger experiment that has been activated now almost 9 years ago, and that gave this particular noise feature that we are studying in a fully quantum model at the moment. So let's start from the very beginning. So most of you probably know the Sagnac effect. The story is that in 1913, Georges Sagnac was really convinced that the light needs some mean to travel, this well-known story of heater. And so he designed a closed loop for the light, and launching light into opposite direction, he would have evidence the dragging of the heater on the light. What he did actually do, he found some difference in the path, but this is not dragging, but it's just because the time of flight depends on photons inside the ring, depends on if the table is rotating, depends on the direction you go. So the Sagnac effect is indeed compatible with the heater hypothesis and does not require relativity. And the point is that Sagnac system correctly calculated the amount of the effect in absolute time space frame. Then what happened is that this effect can be used to measure the rotation actually. So if you this is a time difference in the flight of photon, but can be reverted in a phase difference for a light. And if you have a resonant cavity, it means that the two cavity, the there are two cavities, actually, one in one direction, one the other direction, and the resonances of this cavity are split apart by this Sagnac effect. And so if you have an active medium inside the cavity, the laser medium will see different cavity and will emit at two different frequencies. So you measure the difference between these two frequencies and you retrieve the rotation of the system. Then if you attach this system to a very big rotating object, that is the Earth, you will measure the rotation of the Earth. And actually, the rotation of the Earth contains, if you look at general relativity theory, contain different contributions. One is the Newtonian stuff, so it's the usual rotation we are used to think about, and other are relativistic effects. One of these effects, in particular, the lens steering effect, is called the gravitomagnetic effect. It means that it's exactly the mass current of the Earth itself that makes this effect. This is why it's called gravitomagnetic. It has nothing to do with the magnets, but it's just because it's equivalent to the effect given by charges that travel and current and so on. So this is a very teeny effect, actually. It's 10 to the minus 9 times the main terms, that is the Newtonian term. So, and also it's a bit misaligned with the rotation of the Earth. So this is the Newtonian stuff. This is the lens steering. There are other small effects. So what happens is that these two combine as vectors, and so you have a deviation of the rotation axis and also a change in the modulus. The point is that to measure omega, so the true omega, require a very high sensitivity because you have to discriminate between effects that they have 10 to the 9 times difference, orders of magnitude, 9 orders of magnitude. So we started to think how to improve the sensitivity of the object. The first part is obviously mechanical stuff. You have to have a very rigid cavity with controls and whatever. You have to stabilize the laser emission and so on. But then you start to think how long you have to measure the system to reach the required sensitivity, because this is a continuous effect. It means that you should measure at zero frequency, and for experimentalists, measuring at zero frequency is always a very hard task, because in principle should be infinite time of measuring. So with Ginger, we aim at measuring this effect by a system or a multiple system of gyros, because you have to measure a vector, so you have to reconstruct the different components. So this is a sketch of the planning inside the National Laboratory of the Gran Sasso. So these are the gyroscope. That this is in scale. This is 5 meters by 5, the square dimension of the gyroscope, because the sensitivity depends also on the area. Closer inside the ring cavity, and this is a more from far away. This is a place where we aim to place our device that should go into construction next year, depending on some structural work that they're doing inside the lab. So if they finish in time, we are ready to mount next. So, and here is Gingerino. This is a prototype that actually is in this area of the National Laboratory that's far away from the main experimental halls. So it's a very quiet place. very stable temperature and whatever. There is no anthropic noise in that area. So this has been used for a long time to test the site and to also to test the device itself. It's very nice that this is becoming in during the time a multidisciplinary staff. We have the seismologists and volcanologists that are really interested in this device because the rotation of the system is also connected to seismic noise and so on. So then we have to understand what is the noise limit. So as I told you at the beginning, in principle, this is limited by the shock noise. But how to measure the actual noise level of your device? So first, after a while that we were trying to measure the noise and to get the noise essentially from a deep analysis of the data, we took from the quantum optics the differential measurement. So essentially we took the, okay. So we just decide to take, so what is the standard method to measure the Sagnac? You have a corner mirror and you put a beam splitter or just take the interference in a prism of these two counter-propagating beams and you get one of the output and you see this the sinusoidal signal of the rotation that come out. Then if you take the other one, output of the beam splitter, you can perform differential measurement. These two are out of phase, so you can just track the frequency that the two measure in an independent manner. They are statistically independent, this is for sure, and so the only manipulation that you have on data is to have the Hilbert transform that give you the frequency from a periodic scene. So this is essentially the high frequency part of the noise spectrum. The red curve is the differential measurement and the blue one is the measure from single beats. So as you can see at high frequencies as expected, the two coincide. This is what is expected for a shock noise limited device. But the point is that if you look at the low frequency, the two split apart by orders of magnitude. So we are interested in this area here where the noise gets flat in the differential measurement to understand what's going on here. And this is the Allan division that measure. It means that the Allan division is stand for the ones that is not, are not used to measure frequency. So the Allan division measure the stability of your frequency signal. And this is what is the level of the shot noise expected, that these are experimental. So we are about 20 times below the expected noise level. So there are some open questions. First question is, to what extent this is a quantum effect? And if this is a quantum effect, are there any quantum correlation inside the system, or it's just a mistake in the calculation of the shock noise? What is sure that so far the model that dates back to the late 80s of the last century in the group of Marlin Scarley, they thought that two beams were completely independent, but the two beams are not completely independent because they share the laser medium, and they have cross-talking by the mirrors. When they are reflected by the mirror, you can have some photons that is backscattered in the wrong direction and coupled into the other beam. And this is a well-known feature of ring lasers gyroscope. So you have the backscattering, and the backscattering results in a modulation of the single beam at the Sagnac frequency. So if you look at the intensity of the single beam, you just see a teeny oscillation of the intensity, a periodic oscillation that is at the Sagnac frequency. And this is a signature that the two beams are coupled. So classically, what you do in your data is just you monitor the single beam oscillation, and then you cancel this noise from your data. But what happens to the noise level? This is a classical procedure that gets to the shock noise, not below. Then there is the laser dynamics. The laser dynamics is a complex dynamics, and there are some nonlinear terms. And you all know that nonlinearity gives rise to correlations. So this has to be evaluated in a full quantum model. So the model, so far, the old model gave this expression for the shock noise. So you have the quality factor of the cavity, the perimeter, the area of the ring, the frequency, and the time of observation, and the power loss by the cavity. But this is, this is obtained only if you consider the two beams independent. But these are classical equations for the ring laser. These are, n will, it's a label for, plus n is a label for one direction, and minus n is a label for the backward direction. And this is a multi-mode expansion of the cavity and so on. But what I want to show you that these are forward direction, and there is a coupling classically to the backward direction. There are two coupling. One is a Chi2 coupling that comes from the laser, and this is coming from the backscattering with a certain coefficient. So why do not consider this in a quantum model? So essentially, what you have at the photon, level is that you can have some photon that come back and we couple to the active medium in the wrong direction with the wrong K, and it's amplified and so on, and start to travel in the wrong direction and so on. So, moreover, the ring laser is an open quantum system. You have some leakage, and you have to read the leakage, because what you are actually reading is the signal that come out from the gate. So the principle, the model is essentially that you have two frequencies that you center into the Sagnac frequency, and then you move away 1/2 of the signal, and then this is, sorry, omega 0 is the central frequency of the laser emission, and you split the two modes at 1/2 of the Sagnac frequency, and then you have to account for the environment and for the fact that the laser is made of two isotopes, because if you have only one isotope, it's very difficult to get the emission on different frequencies that will lock inside the laser. So you have two isotopes, and so the gain curve is two curves that are close together but somehow split it. And then you have a backscattering that is a non-conservative photon exchange mechanism. And then you have the laser power here. So this is the free propagation term. These are the two modes, and you have free propagation, standard damping into the mirror, and then you have the atom part of the coupling to the one of the mode and to the other mode, and then you have to add the backscattering. The point is that backscattering preserves the total number of photons, so it's a linear combination of exchange operator. And what is nice that the Hermitian linear combination does not reproduce the synchronization of the phase between the two beams, and while you need a skew Hermitian term to reproduce this effect. What is phase synchronization is essentially a classical effect that you can see also in ring laser. So if you have two clocks on one wall, they will start to synchronize the phase because there is some phonons in the wall that couples the system. And this is a skew Hermitian interaction. It's not an Hermitian one. So it's similar to the one, it's just a pictorial view of the backscattering. So the mirror acts as the wall, and you have the photons that are the two oscillators. So essentially, to keep the Hermitianity of the full Hamiltonian, then you have to consider different baths for different modes. You cannot consider a single bath. You have to consider also that the bar are different, the baths are different. So this give you back the Hermitian of the full Hamiltonian. And so here is the Hamiltonian for one of the modes, and you have to add two different baths for the coupling to the environment. And then you have a coupling, a skew Hermitian coupling plus an Hermitian term with the other mode. And then you have the this more coupling where you see the phase counts for the phase synchronization. But then if you want to put all together the atoms in the backscattering, the expression becomes quite long. So I didn't show the expression in details, but you see that there are many terms, many coefficients, and so the expression is very complex. So what so far we are working at this point. So we have put in set the equation, the quantum Lenderian equation. All the terms have been checked and discussed longly for physics beyond them, and we were able to retrieve the classical equation from the quantum model. So we are in a mood that these equations are right, and we are working at solution in relevant regimes, and then we will linearize the Langevin quantum Langevin equation, possibly or hopefully reproducing the noise we have seen in our device. So these are my conclusion, but I don't think to have to go into details because it's, essentially it's a resume of what I've already said to you. And so there is only one possible conclusion, that work is in progress. And if you are interested, there are positions available on this experiment. Thank you very much.
Alberto Porzio. You mentioned the effect of the scattering following from the optics, which in the interferometer, which is almost ideal mirrors, it's supposed to be a small burst. Why do you consider that most, say, important and think it
Well,
seems like the
nice question, because give me the possibility to explain that our mirror are 5-9 mirrors. So we have lots of 12, 14 parts per million in each mirror. But nevertheless, we have backscattering in the system, because you have a very, huh? No, essentially, the cavity is almost close. Let's talk in this way. So the number of times that each photon reflects on 4 mirrors, it's very high. So even if the chance to be back reflected is very low, it happens. And we see it in the single beam signal. We see the modulation of the intensity. And this is nice because we believe that if the backscattering is the main contribution to the reduction of the noise, because couple the two beams, perfect mirror will be worse manner than the non-perfect mirror. Maybe. We will see. I'm not sure about that. Thank you.
Very much for the next talk. So, you are proposing that the reduction in the shock noise is due to correlation of the noise of the two nodes.
Yes.
The coupling of the backscatter.
Yeah.
Do you think that it would be advantageous to control the backscattering, right? For instance, like very.
Well, actually, what you do is that you control the phase of the backscattering. This is not simple, but it's usual, because you control the perimeter of the cavity. So there is a control, actually, there is a control on the perimeter, and we are setting a control on the diagonals. Because if you think, this is more technical, I mean, if you think that you have a square ring, you have a fabric mirror also on the diagonal. That is not the same quality of the cavity or the ring cavity, because the mirror are set for 45 degrees, but you have still have a good fabric mirror cavity on the diagonal. And if you stabilize the diagonal, you are stabilizing the area of the system, and this stabilize the phase of the backscatter. Not the, I mean, I don't know if you can manage to control the amount of backscatter.
So like very small, directly there.
But anything you insert in the cavity, you lose a lot, because you have a Q of the cavity in the sensitivity. So and anything, I mean, the cavity should be as perfect as possible.
If you can mirror, so maybe you can use either addition pressure, the kind of to have that.
Remember,
Yeah.
I will talk to David about this.
Okay. Well, it's a bad idea.
No, I don't know. Maybe I will talk to David, because he's an expert of membrane.
I explained in time for a very good question. So it's very important. See your point in the logic, you understand it. I would say sensitivity. So just to understand whether you are still saying in a
Well, actually, the sensitivity we reached, it's
going down.
well, actually, our last paper, that's the sensitivity was in the femtoradians range. So it's this is the question I
Basically, I just wanted to gauge whether you expect an increase in sensitivity because of noise, what the ocean noise was actually also the sensitivity, the sensitivity of the system, so the ratio between the noise and the signal. For example,
the point is that this is the limiting noise, but it's not actually the sensitivity you can reach, because this is a differential measurement, but you cannot measure the Sagnac frequency in a differential manner. So you have to measure it in a different way.
Good.